Hello, I am going to be explaining the second FRQ AP Physics problem. So, basically we're given a situation that looks something like this. Let me read the question real quick. So, a 2,510 kilogram car drives along a curve, radius of curvature equals 50.0 meters, which is banked inward at an angle of 30 degrees. The coefficient of static friction between the road and the car is mu s equals 0.43. Calculate the maximum speed in meters per second at which the car does not slide up the ramp. Okay, so first we want to write our objective. So objective, what is that? So that is calculate the max velocity at which the car does not slide up the ramp. Does not slide up. Okay, so now that we have our objective clear, we can figure out what we need to do. Well, we're given that mass equals 2,510 kilograms, radius equals 50.0 meters, theta equals 30 degrees, and mu s equals 0.43. So we have our givens, we have our objective, now we need to analyze. So, first thing we want to think about is conservation of energy or conservation of forces. And this is, friction is a main part of this problem. So we're going to use conservation of forces. So to do that, we got to draw a free body diagram. So we will draw, first we'll do the sum of the y forces, right? So we have here our mass, and then we have normal force, and we have our mass times gravity. And basically what normal force is Newton's third law is for every action there must be an opposite and equal reaction. So basically when there's gravity, there must be an opposite and equal reaction, which is pushing up. Because for instance, this car isn't going into the ground, it's staying still. So that means although there is the force pushing down, there also has to be a force pushing up so that the car stays in this one place. So as you can see, we have our gravity and we have our normal force. And because it's on a slope, our normal force isn't straight up. So in order to have it go along our reference axes, which I forgot to draw, we'll draw that right here, plus x and plus y. We need to break it down into components using our trigonometric triangles. So we can break it down. I should write it like force n. We could break it down into, this is normal force cosine theta, and normal force sine theta. Because theta is that angle there, and you would have to multiply by Fn, because normal force cosine theta equals normal force equals x over normal force, and so x equals normal force times cosine theta. And then now we have our normal force and we have our gravity, but now we need to add friction. So let's do that. So same thing, because it's on a slope, friction is pushing this way upwards. So we have our friction, but it's going at a diagonal. Oh, shoot. So we have our little F, right? But now we have to break it down into components again. So we have F cosine theta and F sine theta. I don't know if you can see it. F. And then, yeah. So now we use our conservation of forces. So, because basically we know that because the object, our mass, isn't moving anywhere, that means all of the y components and x components added together is equal to 0. So sum of force x equals 0 because the mass, the car, isn't sliding up or down. That's the whole point, is we don't want it to slide up or down. And it's definitely not floating up in the sky or, breaking down into the ground or whatever. Hulk smashing or something. So we know that the sum of the forces y equals 0. So using that, we can say sum of forces y equals, and then we have to add all of our y forces, which is gonna be normal force cosine theta minus mg minus friction cosine theta equals 0. It all equals 0 because the car isn't, going up or down. It's staying in place. And then we can rewrite that as normal force cosine theta is equal to mg plus friction cosine theta. And so now what we want to do is we want to isolate our normal force, because we don't know what normal force is. We know that it's the opposite of whatever's going down, whatever's of the downward force, but we don't know what that is. So we want to isolate that. That's our only unknown variable, and we can use that later for our final equation. So but also friction is mu s times the normal force. So we also have to simplify that first before we can isolate anything. Almost forgot about that. That was so our f cosine theta is gonna turn into mu s fn cosine theta. See how I switched the f into the mu s f. And then so now we put all the normal forces on one side. So normal force cosine theta minus mu s normal force cosine theta. Hold on, that's not right. No, it's sine theta. Why? Okay. That is a big brain fart. Okay, let me just change all these, because that doesn't make sense. Yeah, I don't know why I had cosine theta. Yeah, I was looking at the wrong thing. That's that's a mistake on my part. Okay. F sine theta. F sine theta. Oh yeah, no, I just messed that part up. Okay. So we have normal force cosine theta minus mu s normal force sine theta is equal to mg, and now we want to take out the normal force. So normal force parentheses cosine theta minus mu s sine theta is equal to mg. And then we have normal force is equal to mg over cosine theta minus mu s sine theta. Okay. So now that we have that, we can save that, put it in our back pocket. We'll come back to that later. But now we have, so that was the sum of the y forces. Now we have to do the x. And I'm just gonna do another free body diagram just because so everything, it's not all cluttered. So we have our f cosine theta. We have our normal force sine theta. And now we have, so our sum of forces x is equal to fn sine theta minus cosine theta equals 0, right? Because we have our x's and they cancel out, so that's why they equal 0. But now we have to take into account centripetal force. Centripetal force is basically whenever you have an object going in motion on a circular path, and basically the force, when it's on that circular path, instead of just shooting out, what it wants is the centripetal force keeps it in that circular path, so it kind of let me draw this. Why is that black? As the object or the particle moves around, the centripetal force pushes it into the middle. So kind of like this, and it'll keep going around. Well, I'll draw the fourth one just so it's symmetrical. Right. So instead of just shooting out like this, it doesn't want to do that. It wants to keep going. Yeah. I use it for track and field, like when you run a curve, sometimes you want to think about centripetal force to kind of help you get around the curve. Anyways, so now that we have that, so we have our centripetal force. Oh, our centripetal force equation is well, I guess I'll write it out. So basically, centripetal force. Oh, we know force equals ma. That's Newton's second law. And so centripetal force equals m, and then our multiplied by our acceleration. Our acceleration is v squared over r. So now we have our centripetal force equation is centripetal force is equal to mv squared over r. Okay. Now we can say, so our centripetal force is equal to this this whole thing, this normal force sine theta minus of our whole sum of x forces. So it'll look something like this, where you have centripetal force equals normal force sine theta minus friction cosine theta. And so now we can plug in our centripetal force equation to get mv squared over r is equal to f of n sine theta minus friction cosine theta. And now, as you can see, with this equation, that gives us a v that we can solve for. And remember, our objective is to find the maximum velocity. So that's that's kind of where we want to go with this. And so now what we can do is isolate normal force again by doing the same thing. So we have our friction goes to we can plug in our friction equals mu s normal force equation into friction. So we have normal force sine theta minus mu s normal force cosine theta. And now we do the same thing. Take out our normal force. So mv squared over r equals normal force parentheses sine theta minus mu s cosine theta. Let me just make sure I got that right. Yeah, okay. So now we take our normal force from our last equation, plug it in, so you get mv squared r over r equals mg over cosine theta minus mu s sine theta times sine theta minus mu s cosine theta. So now we have a whole bunch of variables, and what we want to do is isolate v in order to complete our objective up here. So once you do that, we'll get v equals m cancels out, divide both sides by m, they just go away. So v equals v equals the square root of rg sine theta minus mu s cosine theta over cosine theta minus mu s sine theta. And now that looks like a bunch of mumbo jumbo, but remember, we have a bunch of givens up here. Look, we have r, we know what r is. We have g, we know what that is, that's gravity. Theta, given up above. And we have mu s, that's also given up above. So once you plug it into your calculator, do a bunch of, calculations and whatnot, then you'll get v is equal to around 31.1 meters per second. And yeah, that's it. I mean, yeah, it's the same thing, just like the last question. You got to break it down into parts. It's the F, the little things like the friction and the centripetal force. But the one, I think a big thing is to also remember that whenever you hear friction, you can think conservation of forces, versus the last problem, which didn't have friction. We were able to use energy. Yeah. I think that's it. All right. Thanks for watching. Like and subscribe.